Welcome back. In the previous segment, we looked at declaring variables, assigning values, and using arithmetic operators in the C language. If these concepts are new and foreign to you, then you might consider looking at the video segments in the course called Introduction to Programming Concepts. This class is kind of assuming that variables and assignment and arithmetic expressions would not be a new concept completely. So in this segment, what we're going to look at is the remaining data types in the C language. We looked at the int and double data types, and those are typically the ones that people would use for whole numbers and floating point numbers or real numbers, unless there's some reason not to. In that case, you would choose one of the other data types depending on what the need is and the reasons for why you wouldn't choose the kind of default ones for declaring numeric variables. And we're also going to look at expressions where you use more than one data type and what the impact of the calculation is in mixed data type expressions. So there are several data types in the C language, and the C language was written originally in 1972. In computing years, that's forever ago. So it's a very old language, and as time has gone by, some people have moved to new languages. The C language is still a very strong language for writing code that's very close to the hardware. So it has evolved, and some of the new data types that have been entered into the language are to account for the changes in hardware that have occurred over the last 40 years or so. So we have a lot of data types to choose from. Mixed data type expressions then become a little bit complex, but the concept of what happens when you have more than one data type in an expression really is the same no matter what two or more data types you're using. What you want to do is to choose the data type that's appropriate for your variables based on the type of data that you have and the size or the magnitude of the values that you would want to store in those variables. And I guess we could point out here that this used to be a critical part of programming when random access memory was very expensive and programs would try to be written. People would try to write their programs using the smallest possible amount of memory to save time and money. But now the processors are so fast and the RAM memory is so cheap, it would be difficult to spend too much time trying to save a few bytes of memory or a few cycles of the processor. So this table shows you the data types that are available to you in C using this compiler, and it's not just a single word data type. That's the first thing you notice. So the one that we've been using most commonly, int, for whole numbers is not even on this list, and I'll explain why. Well, all of the ones except for the last two store integer numbers, whole numbers. The last two, let's look at those first, float and double. These are the data types that you would use when you have a decimal point in your numeric values. So the float data type is the one that people used to use most commonly. It takes 4 bytes of space to store one float value, and it has 6 or 7 places of accuracy. So that's kind of key. If you're doing a calculation that needs more than 6 or 7 places of accuracy in the number, then probably shouldn't be using a float. You should be using a double, which has 15 or 16 places of accuracy depending on what the value is. The magnitude of the float and double is also indicated on this chart. The e is exponential notation. So 3.4e minus 38 means take 3.4 and move the decimal point 38 places to the left. Similarly, plus 38 means move the decimal point 38 places to the right. So you have very, very large numbers or very, very small numbers on the other end that can be stored in a float. But the key is how accurate are those numbers and the magnitude of the values that can be stored in double. You can move the decimal point 308 places. So you picture a number with 308 digits in it, but only the most significant 15 digits are going to be accurate. So large magnitude, but the accuracy still is only 15 or 16 decimal places. So let's look at the integer data types from unsigned char to long int. You can see the number of bytes each one requires on the right of this table. Character or char data type takes only 1 byte of space, and that's the smallest data type that exists in the C language. The range of values is what distinguishes an unsigned char from a char, or you can actually use the word signed char when you're making this declaration. If you need negative numbers, then you would use a char, and if you don't need negative numbers, then you could use an unsigned char. And you can see the difference in the range from 0 to 255 for unsigned, minus 128 to 127 for signed. Now let's look at unsigned short int, unsigned long int, and long int, and the difference among those 4 data types. We've been using just the data type int, and in this compiler that's the equivalent of using a long int, or a 4-byte integer value. In the older C languages, an int variable was 2 bytes of space, and some compilers still do it that way. A Unix-based C compiler, for example, an int variable would be 2 bytes of space. And when they made the standard, it became necessary to distinguish, well, if int could mean different things, what should the standard be? And it was decided that they would introduce the modifiers long and short. So what we really should be doing is declaring long int or short int if we want only 2 bytes of space. Typically people are kind of lazy and they don't do that. They just say int and it defaults to what system they're programming on. Probably not a good practice, and depending on who you talk to, more or less strict on whether you should be using the modifiers long and short. More recently in the language, an 8-byte integer data type was added, and it's called the long int. So the range of values in a long int, minus 2 to the power of 63 through 2 to the power of 63. So very large integer values could be stored in a long int. In some C compilers, modern C compilers, there is another data type called a double, which is a 16-byte double value or floating point value. And the Microsoft C compiler doesn't have one of those. If you declare a double in this compiler, you will get the same thing as a double value. So I don't think you should memorize all of the values on this chart, but I think you should probably have a copy of it handy somewhere so that you don't have to look it up. And you should be able to work with these data types and understand them, what the difference is between them, among them, but probably at this point not memorize them and just get comfortable with what the differences are. So we talked a bit already about mixed data type expressions, and this is when you have an arithmetic expression that has more than one data type, either literals, which have data types, or variables, which obviously have data types. Okay, here we are in the development environment again, and I created a new project called Data Types, and I started a C program called datatypes.c. So there isn't really that much to demonstrate right now, but what I would like to do is to just declare variables of each of the data types and to introduce the operator size of, which shows you how many bytes there are in a particular data type. So let's start with the smaller ones. So when they turn color, you're pretty sure that you've spelled them correctly. So the smallest data type we have in C is the char, or you can say char if you want to. And there's a unsigned char. The largest value you can put in that one is 255. And then if you have a signed char, you can actually write the word signed in C, but it doesn't do anything because the default is signed, so we usually just leave that out. So a char or a char variable C, the largest value you can put in that one is 127. The difference is that you can put negative numbers in a char, so you could put negative 128, but in the unsigned char it can only hold positive values. So then the data type that we've been using up until now, int for whole numbers, should really be specifying what kind of an int, either a short or a long int. And if we say short int, and I'll call that SI, we can start to put larger numbers in there. We can put 32,767. And yes, I did have to turn and look at my page to see that exact number. So I don't have these memorized. And an unsigned short int, I'll call this one USI, just so we can remember it. And you can put in there 65,535. Notice that I don't put any commas in those literal numbers. You can't. They won't compile. So let's just start with those 4. There are 6 more, but we'll start with those and look at how we can check to see how many bytes each one takes up. So there is an operator called size of, and you can put in there either a data type or a variable, and it will evaluate to the number of bytes that that variable is using. So if we say size of unsigned char, that will evaluate to 1. So let's make a variable right up at the top. How's that? Int size. Now I've gone against the recommendation of specifying what kind of an int I want because I'm lazy. So size of unsigned char should be 1, and then we'll watch this value change in the debugger, and let's repeat that a few times. So I'll copy and paste that a few times here, and then replace it with the other variable data types. Unsigned short int, and then short int, and I've got one more than I want right now. So let's compile that and run it. F7 compiles. I hope your machine is a little faster than mine. So we don't have any compile errors, and we don't have any warnings. We didn't ask this program to print anything out, so I'm going to put a breakpoint there. And when we run this in the debugger using F5, or that green triangle pointing to the right, it will run to the breakpoint. And in locals, we will see that we have some variables declared and some numbers put in those variables. The variable size doesn't have anything in it. It actually has junk left over from the last time, and that should help you to know that we have not yet executed this statement. So if we execute that statement, size now has 1 in it because unsigned char requires 1 byte of memory. It shouldn't change when we execute that one. It still has a 1 in it. Now an unsigned short int, it takes 2 bytes of memory, and so does a short int. Let's continue, meaning just allow the program to end and do some more. So unsigned char, unsigned short int, and then unsigned long int and long int. Those should take 4 bytes each. And then we have this odd character, the unsigned long int, and a long int, and a float, and one more, a double. And I think this compiler allows me to ask for the size of a double, and that should prove to us that it's the same as a double. So let's walk through this in the debugger. I prefer to watch it actually happen instead of using print statements at this point, partly because we haven't covered the printf statement up until now, but also because you can make mistakes in the printf statement which will then cause you to think that you have a different result than you actually do. So let's compile with F7, and I have 1 errors. Double double. It does not allow me to ask for the size of a double double. I didn't remember that. I knew that it wasn't useful in this language, in this compiler. I just didn't know if it recognized it as something. Good. So I learned something as well. Now we have 0 errors, and if we hit F5, we can run to that breakpoint and watch the size variable change as we execute these one by one. So an unsigned car is 1 byte, a car is 1 byte, a short int is 2 bytes, and an unsigned and assigned short int is 2 bytes. An unsigned long int is 4 bytes. Remember, it points at the line we have not yet executed. A long int is 4 bytes. Now an unsigned long int is 8 bytes of space. That's 64 bits. A long int is also 8 bytes. A float is 4 bytes of space. And a double is 8 bytes of space. Okay, this is not really too interesting, but make sure that you understand that you can always ask the compiler how big your data types are, and you can also ask it equivalently how big your variables are. So perhaps it's worth it right now to prove that if we put a variable name in the size of operator, we would have the same result. So I'll just change a couple of them and recompile and run to the breakpoint. So the size of an unsigned car, or the variable UC in this case, which has 255 in it, that's kind of a nice feature that you can hover over the variable in the debugger and it will tell you what the current value is. So we have the same result. The size of UC is the same as saying the size of the data type for that variable, which is unsigned car. Okay, let's go back to the slides now and start looking at use of these data types in different kinds of expressions. In the last segment, we looked at the fact that the operators also have a data type, and recall that we did examine the difference between integer and double division. So 10.3, the result is 3, an int, and 10.0 divided 3.0 is 3.3 repeating, which is a double. So these aren't really mixed data type expressions. This is just an example that there are differences in the computation using the different data types. So each of the data types has an accuracy, and the operators that work on those data types have the corresponding accuracy for the data type. So when you're evaluating an expression that uses more than one data type, an arithmetic expression, what we need to do is to make sure that we understand how C will move a value from one data type to another. So an operator can only work on one data type, and that means if there is more than one data type in the expression, we have to move one of the values to a larger data type, and that's called a promotion. So let's look at this very simple example. First of all, double result gets A. A has 10 in it, which is an int. The assignment operator needs to have a data type. So should we pick the int data type or the double data type? Because we've got A on the right, which is an int, and double result on the left, which is a double. C will always choose to promote or go to the larger data type when it has the option. So in this example, the value in A becomes a double, which is 10.0. It's not stored in the variable A as 10.0 because A is an int. 10.0 is stored in a temporary location, which can then be used to evaluate the rest of the expression, which in this case is just assignment to the double result variable. Okay, a demotion is when there's the possibility of data being lost. So in the next example, we have D1, which is a double that has 4.5 in it, and we're going to assign that to result, which is an int. So 4.5 will not fit in result. So what will happen in this case is that the 0.5 is thrown away. When data is lost by demotion, then you'll get a compiler warning. So this is called an implicit demotion because we haven't explicitly said as the programmer that we want that to happen. This is a little bit risky. If you have data being lost during the execution of the code, you probably should have explicitly said it's okay that that happens, and a warning will be generated at compile time telling you that you've written a statement where some information or some data may be lost, and in that case result gets D1. It will compile and it will run, and the value in result will be 4. Okay, let's look at these divisions now. We have A divided by B, which is an int division. The result is 3, and we assign it to the int value result, the int variable result. That's not a mixed data type expression. All of those are ints, including the division operator and the assignment operator. And in the next example, double result gets D1 divided by D2. This is also an easy case. All of the variables and operators in that statement are data type double. So let's start looking at some more interesting cases of mixed type expressions. In this one, we have double result gets A divided by D2. So A has 10, D2 has 3.1. Now we have an int divided by a double. There is no division operator that can work with an int and a double. So C has to make a decision of which data type to use. C will always choose to make a promotion. So the A, which has 10 in it, promotes so that we have a double divided by a double, and the division operator is then obviously double, and the resultant data type is also double, and we have 10.0 divided by 3.1. It's a double value that has accuracy past the decimal. Look at the next example. It's kind of interesting. Double result gets A divided by B. A and B are both int variables, but double result is a double. So what happens in this case? We decide the data type of the operator at the time we evaluate the operator. So A divided by B, that operation happens first. A and B are both int values, so the division happens in int. And the result is 3, which is an int value. Now we want to assign 3 to double result, but we can't do that. You can't assign an int to a double. C decides to promote the int to a double. 3.0 goes into the double result. So you might notice that in this case, if you did 10 divided by 3 and you wanted a double result, you probably didn't want to let the division happen in integer. So 3.0 is no better than having 3, which is the integer result of dividing A by B. Determining the operator data type is a little bit tricky, so we have this slide specifically to address that issue. Look at this example where we have A plus B divided by 2, and the question is, what is the data type of the addition? If you answer the question too quickly, you'll look at A plus B and you'll say, well, the operands of the plus sign are both ints, so that's an integer addition, but it isn't. Which operator happens first? The division happens first, so we have B divided by D2. B is promoted to a double, so the division is a double, and the result of the division is also a double. So now the right-hand operand of the addition, we have A plus a double, so the data type of the addition is also going to be double. And the result of that is a double, and then the assignment operator happens in double, which is there is no casting required, no promotion or demotion. So you need to know the order of operation as it's happening in the expressions to be able to determine what is the data type of the operators. You can have one statement in C where there are different divisions done in different data types, an int division and a float division and a long division, all in one statement, depending on the operands of each of the respective division operators. Probably not good programming practice to start doing things that are that complicated, and probably for no good reason. So let's do a short demo of the things that we just looked at with different data types. I've made a new project called Mixed Type Expressions and a C program called mixedtype.c in that project. Now I'm just going to declare some variables and put some values in them for purpose of using them in this demonstration. A result variable that doesn't have anything in it, and then a few double variables. D1 4.5. Okay, the first example that we had in the slide said double result gets A divided by D2, and I'm looking at slide 3.5 in this case. So this expression, this statement, looks like we have two operators, an assignment operator and a divide operator. And there are actually three. One of them is implicit. So when we divide an int by a double, then we have an issue that the operator will only work with like data types. So A has the value 10, an int, and D2 has the value 3.1, which is a double, and we cannot have an int divided by a double, but we can have a double divided by a double. So C will choose to promote this variable A, or the value in the variable A, to 10.0, store that in a temporary location that we don't get to see, and then do the division in double. So let's compile this and run up to that breakpoint. I assume that I haven't made any errors here. And double result has a huge negative number in it, which is junk right now because we haven't executed this statement and assigned anything to it yet. So let's execute that, and we find that the result is a floating point number, which is what we wanted. So the reason that this is important is because there's something happening that you don't see. The variable A has 10 in it, and the variable D2 has 3.1, and when you do the division with mixed data types, C needs to decide what data type to use. So if you look back on that slide 3.2 of the data types, those are in order from smallest to largest, and C will decide the larger of the two data types when it decides what kind of an operation it's going to do. Here's something else that's interesting. While we're here, we talked about the accuracy of double and each of the data types. We put 3.1 into the variable D2, and now when we look at what value is in it, we find that it has 3.1, a whole bunch of zeros, and then 1. What is this 1 doing here? Well, we're showing more places of accuracy than there are accuracy in this data type. And that's done intentionally so that the programmer can see that we actually, in storing of floating point numbers, we actually have an approximation of a certain accuracy. So 3.1, which seems like a pretty simple number to store in a variable, is not stored accurately. It has this little error down here, and I'm not going to count all of those, but I assume that that's the 16th place, counting the 3. It might be the 15th, I'm not really positive. Okay, let's put another expression in here. I just hit F5 to let this program finish naturally. And let's write another expression. Double result, A plus B divided by D2. And the question here was, what is the data type of the addition? And it looks like this is going to be an integer addition, but it really isn't, because the division has a higher precedence, so this happens first, and the resultant data type is double. So we have B, which is an int, promoted to double for the purpose of the division, and the result of the expression is the same data type as the data type of the operator. Let's go back to the slides now and talk about data type casting. Well, sometimes we did mention before that the programmer should indicate that it's okay that data is to be lost, but I didn't give you any way of doing that. So we have something in C called a cast operator, and casting happens either implicitly, meaning that the compiler does it for you, or explicitly, meaning the programmer puts the cast operator right in the code. So here's an example. Int variable gets double variable. That's what we had before. Assigning a double value to an int variable would result in loss of data. So the decimal point and everything after it is thrown away. So when there's a demotion, the compiler will generate a warning message. And the programmer, if you really wanted to do that, if you really wanted the integer part of that number stored in an integer variable, then you should have used an explicit downcast operator. So here's your first explicit cast operator. You put the data type inside of parentheses and put it in the expression. So a cast operator has one operand and it grabs onto what's on its right. So int variable gets int double variable. The first thing that happens is we take the double variable and we extract the integer part of it, the part before the decimal. And that means that that int value is what will get assigned to the int variable. That's what would have happened anyway, except the compiler knows now that that's what you meant to do, and you accept as the programmer that some information may be lost during the execution of that statement. Upcasting is similar, and almost all the time you would allow upcasting to happen implicitly. So if you have a plus d, the a would be upcast to a double, the int would be upcast to a double, and without any operator and without any warning message, because no data would be lost in that case. So almost always you allow the upcast to happen implicitly. There's a couple of cases where you have to upcast explicitly, and this is one of them when you have an integer division and you don't want it to be an integer division. You can upcast one of the operands to a double or a float or whatever you want, and that will mean that the division will happen in the floating point data type. So let's look at this. Result gets double a divided by b. What's the first thing that happens? The cast operator takes the value 10 and stores it in a temporary location as 10.0, a double value. Then what happens? We've got a double value divided by b, which is an int value. We can't have that, so there's an implicit upcast of 3 to 3.0, and now we have two double operands on the division operator, and the division happens in double and the resultant data type is also double. Okay, we're going to demo some casting operators, and what we had looked at in this example before was called implicit casting. So when we had b divided by d2, we had an implicit upcast in order for the division operator to have a double divided by a double. Sometimes we have to use explicit cast operators. For example, if we wrote result gets d1. Now, in the C language, we don't need to have an explicit cast operator there, but the compiler will generate a warning. So look down here. It will succeed in compiling, and we can run this program. But when we have these warnings, conversion from double to int, possible loss of data, clean programmers, whatever that means, probably wouldn't allow that to happen. They would explicitly say, I know that there's going to be data lost potentially, so I'm going to downcast the value that's in D1 before I assign it to the double variable. So let's recompile that with the explicit cast operator in place. And we have 0 warnings. So the exact same thing would happen when we ran the program with or without that cast operator. Sometimes a cast operator is essential to change the behavior. So let's look at
double result gets a divided by b, and we looked at this one in the slides. A divided by b, those are both integers, so 10 divided by 3 is 3. The integer, 3, which would be promoted implicitly to 3.0 to be assigned to double result. But that's not really what we want. If we want to have the floating point result of 10 divided by 3, we don't want to lose the data, then we can write an explicit upcast. So here's what happens. We have the variable a has 10. We take that value and temporarily store 10.0 in an unknown location. We don't have access to it. It's just for use in the rest of this expression. And then we have an implicit upcast on the other side. Because we have a double on the left, then C will promote this one to a double on the right. And now we have a double division. So if I put a breakpoint there and prove this to us all, that 10 divided by 3 in double is a double value, F5 will run to the breakpoint, and if we execute that one line of code, then double result now has 3.33333 up to its degree of accuracy where we have this 5. But don't worry about it, that's as accurate as we can divide 10 by 3 in the data type double. So you might be wondering, why didn't we explicitly cast this one as well? And you can. In general, it looks funny. You probably would allow the compiler to do a promotion without explicitly asking it to, when it will. So upcasting the one on the left is what you would expect it to do. This is also valid. Upcast the one on the right and allow this one to implicitly upcast, but that also looks kind of funny. It will to you after you've done it for a while as well. What you don't want to do is put parentheses here. What will happen now? Well, we have a divided by b happening before the cast, so a divided by b is the integer 3, and then upcasting it to a double, it's too late. We still would have 3.0. So the cast operator grabs onto one thing on its right, and it might be a whole expression like this, the result of evaluating this expression, or it might be one variable like that. So this is the most common way that you would see someone explicitly upcasting so that a division in this case would happen in the data type that you want. Here's the more interesting arithmetic expression that uses different data types, and these start to get complicated. Maybe there's a reason for writing something like this if you're a mathematician. So let's look at what happens when, more than what the value of the result is. So what happens in parentheses comes first. So b modulus a will happen first, and then d1 times a. And there's an implicit upcast here. So we have a double times an int. That multiply will happen in double. That modulus happened in int. Then what happens? The unary double does an upcast, then the multiply, and then the addition. And finally the assignment. Until you get used to this, and I guess these will not ever be easy to just look at, you can always draw what's happening. I mean, do it the way I did it on the slide, where you mark this one out first and calculate its result, and you work the equation from top to bottom. as you're solving it. You shouldn't try to do things like this in your head. It's just not worth it. Okay, let's go back to the slides and sum this up then. You might be figuring out that these expressions can be arbitrarily complex, and you probably shouldn't make them more complex than they need to be, then someone else could easily interpret what you've done. Sometimes people doing mathematical programming will have fairly complex arithmetic expressions and use one-letter variable names. So depending on what kind of programming you're doing, your code might look a little bit different. If you're a mathematician, you might start to write expressions like the one on this slide, and we have to be able to interpret exactly what happens to understand what the result is intended to be. So when you look at this expression, first what happens is inside the parentheses. So b modulus a happens first, and that's 10 modulus 3, which is 1. And then the other set of parentheses on the right, d1 times a. Before we can do the multiply, we have to implicitly upcast the value in a. So now we have d1 times 10.0. d1 is 4.5. 4.5 times 10.0 is 45.0. And what happens next? The upcast operator, the explicit upcast, changes 1 into 1.0, then the multiply, resulting in 3.0, and then the addition, 3.0 plus 45.0 is 48.0. And finally, an implicit downcast, which is probably not a good idea, and maybe shouldn't be in this example, but this is fairly common what people do, even though they shouldn't. We're allowing 48.0 to be implicitly downcast to 48, and that's because the result variable is of data type int. Here are some practice statements, and what I'm hoping is that you will actually go and declare these variables in a C program and verify the answers that you would calculate with a pencil. So it's important that you get used to these fundamental parts of programming, that you can evaluate expressions that include mixed data type expressions using upcast and downcast operators. Well, here's a brief summary of what we covered in segment 3 and what I'm hoping that you have an understanding of from the material in segment 3. We've looked at all of the data types in C. It can be kind of overwhelming because there are so many this early in the semester, but this is all that there will be. The char data type is used either for small numbers or for numbers that represent the ASCII code of characters. Can be used for either. The size of operator that we saw used in the programming demonstration is a very important operator in C, especially since not all C compilers are exactly the same in their data types. So if it's important that you know how many bytes are available, you might ask at runtime, what is the size of this data type, so that if your code eventually moves to another machine, it will still work correctly or have a good chance of working correctly. So the choice of the data type is depending on what kind of data you have, whether you need to store character or real data or integer data, and how large the values might be that you're computing with. So you don't want to waste memory, but you don't want to be so stingy with memory that it might lead to a bug, and the bug would be more costly than any wasted memory that you might have had by picking one that's too large. The unsigned modifier is on the integer data types only. It's not for float and double. So unsigned allows you to use positive values in your variables, and that gets you a different range from 0 to a number, as opposed to a range of values where 0 is in the middle and you have negative and positive numbers. So mixed data type expressions we looked at length, and we described the cast operators that can be used to temporarily change the value so that it will be computing in the data type that you need. And the best example is that if you have an integer division and you need it to happen in double, then you must upcast. Not only variables have a data type, but operators and literals also have a data type in C.
and they work pretty much the same way. You have to be ready that if you use a double literal in an expression, that will upcast an int to a double if it's used in a mixed type expression with an int. People don't usually think of operators as having a data type, but they do. And operators need operands of the same data type. The data type of the operator is determined at the time the operator is to be executed. So you may have more than one division in one statement where each division is in different data types. So a statement doesn't have a data type. An operator within a statement has a data type. So C will always choose to promote your data types in mixed data type expressions. And it does this so that you won't lose data. It won't throw away data without telling you about it. And if you need to demote a data type, a data value, then you should do that explicitly with an explicit cast operator to demote. And that's like saying, I as the programmer accept that some data may be thrown away in this expression. And typecasting is not to be confused as changing the value in a variable. So typecasting takes the value in the variable and puts it in a temporary location with the new data type to be used to evaluate the rest of that statement. And I'll say the same thing I did at the end of the last segment. This is a little bit boring. It's a lot of detail, but it's foundation for what we're going to do. And I want to get this out of the way early, and you can come back to it and review if you feel like going faster in the segments to get to the more interesting stuff. And I'll see you in the next segment.